Welcome back to the eLearning Core 3 Fixed Income Analysis, Session 2.2. In this session, we will figure out if the yield curve has something to say about future interest rates. The main learning goal of this session is to understand the information content of the term structure for future interest rates. Before we further investigate the yield curve, let's recall how to compute the yield to maturity of zero coupon bonds and how this relates to bond valuation. The yield curve is derived from zero coupon bonds. As you might remember, zero coupon bonds make a single payment at maturity and pay no coupons in the meantime. To illustrate this in greater detail, let's have a look at the table and consider a zero coupon bond with a maturity of 3 years. The bond has a price of $816.30 today, and investors receive a single payment of $1,000 after 3 years. Solving this equation for R implies that the yield to maturity for a 3-year zero coupon bond corresponds to 7%. The information contained in the yield curve can now be used to value coupon bonds. For that purpose, suppose there is a 3-year 10% coupon bond with a face value of $1,000 and annual coupon payments. Using the present value formula to find the bond price, together with the information from the yield curve, implies a bond price of $1,082.17. Note, in this context, that each cash flow payment in the corresponding year is discounted by the corresponding yield to maturity derived from zero coupon bonds. Based on this bond price, the yield to maturity for the 3-year zero coupon bond can be computed by solving the bond valuation formula for Y. Another way to think about the coupon bond is as a portfolio composed of 3 zero coupon bonds, where the yield to maturity of the coupon bond is a weighted average on the 3 zero bonds. In order to see what the yield curve has to say about future interest rates, let's assume for simplicity that there is no uncertainty in the economy. This means that with no risk, all bonds must offer identical returns, or investors will bid up the price of the high return bond until its rate of return is no longer superior to other bonds. In this context, an upward-sloping yield curve can be understood as evidence that short-term rates are going to be higher next year than they are now. To understand this claim, consider two 2-year bond strategies. The first strategy entails buying a 2-year zero, offering a 2-year yield to maturity of 6%, and holding it until maturity. The 2-year zero has a face value of $1,000, which implies it is purchased today for $890. Now consider an alternative strategy. Invest the same $890 in a 1-year zero coupon bond with a yield to maturity of 5%. And when that bond matures, reinvest the proceeds in another 1-year bond. Note that the interest rate the 1-year bond will offer next year is denoted as R2. The two investment strategies introduced previously must provide equal returns, since neither entails any risk. From this insight, it follows that the outcome of each investment strategy after 2 years must be the same. If this condition is violated, an arbitrage opportunity would arise. Next year's interest rate will be found by solving the no arbitrage condition under complete certainty for R2, which implies an interest rate of 7.01%. So we recognize that under certainty, by rolling over 1-year bonds for 2 years, the same investment outcome can be achieved while holding a 2-year bond. Summarizing the implication of the previous analysis and to make a distinction between yields on long-term bonds versus short-term rates, the following terminology is used. The spot rate is the interest rate that prevails today for a time period corresponding to the zero's maturity. The short rate for a given time interval, say 1 year, refers to the interest rate for that interval available at different points in time. From the no arbitrage condition, it follows that the spot rate is a geometric average of its component of short rates. For example, the 2-year spot rate is a geometric average of short rates. To illustrate this by example, the 2-year spot rates is a geometric average of the short rate in year 1 and the short rate in year 2. What can we now infer from the slope of the yield curve in terms of future interest rates? An upward sloping yield curve implies higher future short-term interest rates. To see this, note, when next year's short rate R2 is greater than this year's short rate R1, the geometric average of the two rates Y2 is higher than today's short rate and vice versa. We have now a basic understanding of how to infer future short rates from the yield curve of zero coupon bonds for a 2-year period. However, it is straightforward to generalize this approach by equating the total return on two n-year investment strategies. For that purpose, we buy and hold an n-year zero coupon bond versus buying an n-1 year zero and rolling over the proceeds in a 1-year bond. Given the observed yield curve, we can solve this equation for the short rate in the last period. The short rate in year 3 is computing using the yield to maturity of year 3 and year 2. Substituting in the numbers implies a short rate of 9.025%. Since interest rates are uncertain, we call the inferred interest rates the forward interest rate rather than the future short rate. This is due to the fact that we don't know if the future short rate will actually prevail in the future. We should think of the forward rate as a forecast of the future short rate. To emphasize this point, we write the future short rate in period n by Fn to make clear that it is indeed a forward rate. After having carefully studied session 2.2, please start with the review questions.